Hello and welcome back. In this video, we're going to work out this Precalculus Midterm 2 exam that you see on the screen. This test covers section 3.1 all the way to 5.2 of our text. Feel free to look at the PDF version in the description box first, work out the questions, and then you can check them with my answers. So let's dive into the first question. Okay, so for number 1, we're going to find the range of this function, and we're going to express the answer using integral notation. So if you look at this function that we have, this is like negative x squared minus 6, as the leading term is negative x squared. So roughly sketching, it's a parabola that looks like this. It's going facing downward parabola. So the range would be negative infinity all the way to that point right there, which happens to be the vertex, the y-coordinate of the vertex. So we're going to go ahead and figure out what that is. Using the formula, the vertex of a parabola, the x-coordinate of it is given by x equals negative b over 2a. So by looking at this quadratic, we know our a value is going to be negative 1. That's the coefficient in front of x squared. B value is the coefficient in front of the linear term. That's negative 6, and c is 0. So plugging this into our formula, we have negative 6 over 2 times a, that's negative 1. And this would give us positive 6 over negative 2, and that would give us negative 3. So this maximum value happens at negative 3. Let's find out the y value. So for that, we simply plug this into our original function. So we want f of negative 3, the function evaluated at negative 3. That would be negative x squared, so x is replaced with negative 3 squared minus 6 times negative 3. So negative 3 squared, that's positive 9. Because of the negative in front, that makes it a negative 9. And then negative 6 times negative 3, that's positive 18. And then when you perform the computation here, you'll get positive 9. So there you have it. That's the maximum value of this function. So that means the range of f, it's going to be negative infinity, since it's facing downward, all the way to this value 9, including that value 9. So this is our range. For number 2, again, we have another quadratic. So first thing you want to do is look at the leading term, which is positive x squared. So you're looking at a parabola that looks something like this, roughly sketched. So this is going to have a minimum value. So we're looking for the minimum in this case, not maximum. Maximum would be if it was facing downward. So how do we do that? Well, again, you can use the formula we did for the previous problem. Find the x-coordinate, plug it into the function to figure out the y-coordinate. So again, the vertex, we know it's given, and the x-coordinate is given by negative b over 2a. So for this particular parabola, a is 1, b is negative 6, and c is 3. So let's substitute those into our formula. We got negative 6 over 2 times 1. That would give us positive 6 over 3, which positive 6 over 2, and that would be 3. So we need the y value, so I plug 3 into the original function. So we get 3 squared minus 6 times 3 plus 3. And we evaluate. So 3 squared, that's 9, minus 6 times 3, that's 18, plus 3. And then now we can add them up. So 9 plus 3, that's going to give us 12. And then we subtract away 18, that's going to give us negative 6. So this value, the minimum value would be negative 6. So the minimum value is negative 6. Value meaning you want the y-coordinate only, not the x-coordinate. It occurs at 3, but the value is negative 6. All right, moving on to the next problem, number 3. So we're going to evaluate this by using, you can use the definition of logarithms, translate it into an exponential, or you can use the property. I'm going to rewrite this, the input. So you can write it as log base 3 of, so I'm going to write that as, first I'm going to write it this way, 1 over 3 to the power of 1/2. And then this can be written as the log base 3 of 3 to the negative 1/2. And then we know by one of the properties, this is equal to just what's in the exponent, negative 1/2. So there you have it. That's one way to do it. Another way to do it would be to simply use the definition of logarithms. So here's an alternative way to see the same result. So by using the definition of logarithm, so we know that log base a of x is equal to y, then this can be written in exponential form as a to the y equals x. So in our case, we have log base 3 of 1 over square root of 3, call it x. And then our base is 3, so this can be written as 3 to the power of x is equal to 1 over square root of 3. And again, square root of 3 can be written as 3 to the 1/2. Raise it on the numerator, so it'll be 3 to the power of negative 1/2. And then the only way this equation is true if their exponents are equal, so x has to be negative 1/2. There you have the same answer, but approached differently. First, I use the property. The second, I use the definition. For number 4, we want to determine if the statement is true or false. Well, definitely it's false, because the only way this statement can be true if you had log of a over b, just like that. Not the way we have it in the problem. If you have log of a over log of b, well, that's just what it is. But if you have log of a over b, then this is equivalent to log of a minus log of b, when a and b are positive. So that's why the given statement is false. Number 5, we're going to simplify this. So we're going to use the laws of logarithms to combine first. So I see a subtraction between two logarithms. So this is kind of using this property I wrote right here, the laws. We can join them into a quotient of their inputs. So this is log base 2 of 144 divided by 18, using the laws of logarithms. Now 144 over 18, that's 8. So this is equal to log base 2 of 8. And then you can solve it by using definition, set it equal to x, and then solve for x. So by using the definition, we can say that by definition, this is equal to 2 to the power of x equals to 8. And then you play around with the numbers, figure out 2 to the what power gives you 8. We know that's 3, so x has to be 3. In other words, log base 2 of 8 is equal to 3. Now let's take a look at number 6. We're going to be solving this equation. So first thing you want to do is isolate the term with logarithms. So I'm going to go ahead and subtract 1 from both sides. So we get log base 3 of x plus 1 is equal to negative 4. And then by using the definition, this is 3 to the power of negative 4 equals x plus 1. So the input is treated as one variable. So for x, so this is 1 over 3 to the 4th minus 1. Subtracting 1 from both sides, that's equal to x. And then 3 to the power of 4, well, that's simply 81. So I got 1 over 81 minus 1 is equal to x. Put them in common denominators. You can write 1 as 1 over 1 and then multiply it by 81 over 81. You'll have 81 over 81, and then perform the subtraction. 1 minus 81, that's negative 80 over 81. That's what x is. Now we need to check our answer so that way it makes sense. So when you're checking your answer, you plug this into the original and make sure the input of the logarithm is positive. So we have 1 plus log base 3 of x is negative 80 over 81 plus 1. So we just need to make sure that this value is positive. So this is positive. So is this equal to negative 3? Well, we don't have to complete the check fully. You just want to make sure the input is positive. So negative 80 over 81 plus 1, that's 1. You can write it again using the denominator, 81 over 81. So you'll have 81 over 81. That is equal to 1 over 81. Check, it's positive. So yes, this is a solution. So you can claim this is a solution. So make sure to always check your answer if you're solving a logarithmic equation. For number 7, we're going to be solving another equation. This is an exponential equation. So we're going to go ahead and multiply both sides by 1 plus e to the negative x. On the left-hand side, you have 10. On the right-hand side, you have 2 times 1 plus e to the negative x. Now divide both sides by 2, so you'll have 5 is equal to 1 plus e to the negative x. And now here I can subtract 1 from both sides, so I will have 4 is equal to e to the negative x. And now you can take natural log on both sides. So then you'll have ln of 4 on the left side. On the right side, you'll have just negative x. And then multiply both sides by negative 1, so you'll have negative ln of 4 is equal to x. So there you have it. This is the value of this problem. Now, if you want, you can also rewrite it this way. So think of it as there's a negative 1 in front of ln of 4. So raise that as an exponent for 4. So you'll have ln of 4 to the negative 1 power, which is same thing as ln of 1 over 4 is equal to x. You can also write that as an answer, whichever way you prefer. Both of these are equivalent. Number 8, we're going to solve this exponential growth problem. So we see that we're going to be using the growth model, which is p of t is equals to some p naught e to the rt, where p of t is the amount at any given time t, p naught is the initial amount or the amount you were starting with, r is the rate of growth or decay. It depends on the problem, and t is time. So a culture of bacteria starts at 4,000 bacteria. So this is your initial amount. So let's call that PO. After 1 hour, the count is 5,000. So it grows. So it's a growth problem. So this sentence right here, you can write this as the amount after 1 hour is 5,000. P of 1 is 5,000. How many hours will it take for the bacteria to double? So before we answer that question, we need to figure out R. So using this information, I can set this equal to my formula. P naught is equal to e to the RT. So we can write this as 5,000 is equal to the initial amount, that's 4,000, e to the r, we don't know, t is 1, because when t is 1, then the amount is 5,000. So that's how you use this piece of information that's been given to you. Divide both sides by 4,000, so you'll have 5 over 4 is equal to e to the r. And then natural log on both sides, you'll have r is equal to ln of 5 over 4. Now, once you figure out r, let's figure out the model. So then our p of t, the amount at any given time t, is equal to the initial amount, which is 4,000 times e to the r, that's ln of 5 over 4 times t. Now, every time you have ln and e next to each other like this, using one of the property, you can simplify them. This can be simplified as 4,000 times 5 over 4 to the power t. So the t still remain as an exponent. So this is the simplified model we can use. Now we can answer the question, how many hours will it take for the number of bacteria to double? So we want p of t to be double the amount. So it's 2 times the initial amount is equal to the initial times 5 over 4 to the power t. So we want to look for time. What is t? So t is your question mark. Think of it that way. Now let's solve. So divide both sides by 4,000. So you'll have 2 is equal to 5 over 4 to the power of t. Now to bring down the power or the variable you're solving for, which happens to be an exponent, you need to take natural log on both sides. So we take natural log on both sides. On the left side, we have ln of 2. On the right side, we have ln of 5 over 4 to the power of t. And now t can come forward by using the laws of logarithms. The t will be right here. And now we can simply divide both sides by ln of 5 over 4. You get the time it takes to double. So the time would be ln of 2 divided by ln of 5 over 4. So that will be the time. Here's number 9. We want to evaluate tangent of negative 5 over 4. So we're going to be using the identity that if you have tangent of negative theta, this is equivalent to negative tangent of positive theta. That's one of the very useful identity to use when you're working with a negative angle. So I'm going to use that identity, so I can just write this. The equivalence would be negative tangent of 5 pi over 6. And now I'm trying to see which quadrant 5 pi over 6 lies on, and then I can use the reference angle to replace that angle with. So 5 pi over 6, if you want, you can rewrite it this way. So 5 pi over 6, let's see. So I can write it as 3 pi over 6 plus 2 pi over 6 because 5 can be split into a factor of 2 and 3. Then I simplify these numbers right here. So 3 over 6, that's 1 over 2. So pi over 2, and then 2 over 6, that's 1 over 3. So pi over 3. So now I know how to sketch this. So pi over 2, that's 90 right here from standard position. Pi over 3, that's 60 right here. So that's where this angle lies. This is 5 pi over 6. All right, so now we need to figure out its reference angle. The reference angle for this angle will be this right here. That will be the reference angle. Let me call it reference theta. Now we should also remember that tangent in the second quadrant is negative. So from this acronym, if you remember ASTC, only sine and its reciprocal is positive. Any other trig functions are negative. So this will be negative. So you'll see the negative will cancel out tangent of its reference angle. So let's find the reference angle. So the reference angle in the second quadrant will be pi minus the given angle, that's 5 pi over 6. Put them in common denominator, you'll have pi over 6. So there you have it. This is equal to positive tangent of pi over 6. And tangent of pi over 6 is square root of 3 over 3. So that will be the value for tangent of pi over 6. All right, for number 10, we want to find the terminal point on the unit circle determined by this angle. All right, let's draw the unit circle. So unit circle is a circle centered at 0, 0, radius 1. Let's suppose this is the unit circle, not drawn to perfection, but at least a circle. So negative 3 pi over 4. So negative means you're going clockwise from standard position, meaning positive x-axis. So from here, we're going to go clockwise. So negative 3 pi over 4, let's see, where is that? So 3 pi over 4, you can write that as 2 pi over 4 plus pi over 4, because that's 3 pi on the numerator. So pi over 4, that can be simplified as pi over 2, and then just pi over 4. Now pi over 2, we know that's 90, pi over 4, that's 45. So let's go 90 and 45 from negative direction, clockwise direction. So this is negative 90, negative pi over 4, somewhere right here. So we want to figure out what this point is. This point. So P, which has the coordinates x, y. Now, since it's in the third quadrant, your x direction is negative, y direction is also negative. So these points will have negative coordinates. So that's how you rewrite the angle. That's how you draw it. Now let's figure out the values. So we want the point, which has the coordinate negative x, negative y. So negative 3 pi over 4 has the reference angle, this right here. So that is the reference angle. So we can find the reference angle. We know the reference angle is 45 degrees. So this would be negative cosine of 45 or pi over 4, and negative sine of 45, that's pi over 4. And then we figure out these from our memory. We know that cosine of 45, that's root 2 over 2. So this will be the point, negative root 2 over 2. And for sine, same thing. So it'll be negative root 2 over 2. So that will be the terminal point determined by the angle negative 3 pi over 4. And for the next problem, we're going to find the degree measure of this angle, the negative 5 pi over 2. You multiply this by 180 degree divided by pi. So then the pi cancels out, your answer is in degrees. So you will have 5 times negative 5 times 180 degree divided by 2. So if you do 5 times 180 degree, that's 900 divided by 2. This is about negative 450 degrees. Okay, so for number 12, we're going to find tangent theta if you're given the following condition. So we're given sine theta to be negative 12 over 13. So we know that sine theta is negative 12 over 13. And we know sine happens to be opposite over hypotenuse when you construct a right triangle. So let's take a look at where this is. So here's our xy plane, and we know theta is in the fourth quadrant, so it's right here. So you construct a right triangle that looks something like this. And theta is always coming out from the origin, just like that. So sine is opposite over hypotenuse, which makes this length -12, and this is 13. So we use Pythagorean's theorem to figure out what this is. So we know that a squared plus b squared, which are the legs, is equal to c squared. That's your hypotenuse. So let's suppose -12 is our a, so that's -12 squared plus b squared, because we're looking for another leg of this triangle, and hypotenuse is 13 squared. So we got 144 plus b squared is equal to 169. So then b squared is equal to 25, which makes b is equal to +5, because negative wouldn't make sense. It's in the this is along the positive x-axis, so we'll take the positive value of the square root. So b will be this value. This is 5. All right, so now how do we read off tangent? Well, tangent theta, we know that's opposite over adjacent. So here's our opposite length, here's our adjacent length. So this would be -12 over 5. So that would be the value for tangent. Now for number 13, we want to find, so the point P is on the unit circle. The x-coordinate of P is -2 over 7, and P is in quadrant 2. So this point is located in quadrant 2. We want to find the point x comma y. So we need the y-coordinate of this point. So let's suppose we have a unit circle. Let's draw that. So here's our xy plane. Let's suppose this is the unit circle we're looking at. And the point is located on the second quadrant, so maybe somewhere right there, -2 over 7. So we know the x-coordinate of this point, that's -2 over 7. We're looking for the y-coordinate. Now, since it's in the unit circle, we know the equation of the unit circle is x squared plus y squared is equal to 1. So if you're looking for one of the coordinates, we'll simply plug in what's been given. So we're given x coordinate. Let's plug that in. -2 over 7. So if I substitute x for -2 over 7, I get -2 over 7 squared plus y squared is equal to 1. And now let's work it out. What will this give us? -2 over 7 squared, that's 4 over 49, plus y squared is equal to 1. Subtract 4 over 49 from both sides. So we got y squared is equal to 1 minus 4 over 49. Now put them in common denominators. So you multiply 1 with 49 over 49. So we get 49 minus 4 over 49. So now if you do 49 minus 4, you will have 45 over 49 is equal to y squared. Well, now to solve for y, we take the square root on both sides. So that means y is equal to plus and minus the square root of 45 over 49. Sorry, this is too squeezed over there on the side. So let me just rewrite this. This is 45 over 49. And you can rewrite this in simplified form. Square root of 45 over 7, plus and minus. Now, since it's in the second quadrant, the y-coordinate is positive. So we'll take the positive square root of 45 over 7. Now, 45, I can simplify that. So this can be simplified as a square root of 9 times 5 over 7. And then square root of 9 is 3. So we can reduce that further into 3 square root of 5 over 7. So the y-coordinate is going to be the positive 3 square root of 5 over 7. So that will be the y-coordinate of this point. It's positive. For number 14, we want to find an angle between 0 and 2 pi that is coterminal with 51 pi over 2. Okay, so 51 pi over 2, let's see how large that is. So we have 51 pi over 2. I'm going to go ahead and simplify this. So 2 does divide 51, but it has a remainder. So if I just write that as 50 pi over 2 plus 1 pi over 2. That's 51 pi over 2. And now 2 divides 50 evenly. So this would be 25 pi plus a pi over 2. So 25 pi, well, that's an odd multiple of pi. So we know that it's going to be right here. So if you just write it like this, so 25 pi will just mean that you're going around multiple times, and then you end up starting from standard position right here, and then pi over 2, that's just 90 more right here. So that's where this angle terminates. It just goes around along the unit circle multiple times, and then that's where it terminates. So we want the angle that's coterminal with this. Well, you can keep subtracting 2 pi from 51 pi over 2, or you can simply look at how much we have traveled from 0 to get to the position we're at right here. So we know that this is pi, and then we went pi over 2 more. So we do pi plus pi over 2. So the angle that will also lead you in the same place between 0 and 2 pi. So we can say that our coterminal angle, it's going to be pi plus pi over 2. So that's going to give you 3 pi over 2. So 3 pi over 2 is in the same position as 51 pi over 2. And this angle is within the restricted boundary that we wanted, which is 0 to 2 pi. So that's why that will be the coterminal angle with 51 pi over 2. Okay, now for number 15, we want to find the length of the arc that subtends the central angle of 3 pi over 4 in a circle of radius 10 centimeter. Let's draw a picture. So here's our picture. Let's suppose this is the circle, and let's suppose this is the angle. So this is 3 pi over 4, and we know that the radius is 10 centimeter. Let's call this 10. We want to know what is the length of this arc right here. That's what we're going to look for. Let's call that S. So we know that this arc is equal to r times theta, where theta has to be in radians. And we already know that theta is in radians. It's given 3 pi over 4. Let's just substitute. So this would be 10 times 3 pi over 4. That will be S. Now you can simplify the numbers. So 10 and 4, you can reduce that by 2. So you'll have 5 times 3 pi over 2. And then this would give you 15 pi over 2. So that will be the length of this arc. Now let's take a look at the next problem. So we got it to evaluate cosine of negative 150 degree. So we can use the property, or you can find the coterminal angle. There are multiple ways to do this. I'm going to use the property. So use the property that if you have cosine of negative theta, that's equivalent to cosine of positive theta. So that's the property or the identity I'm going to use to simplify this, since my angle is negative. So cosine of negative 150 degree is same as looking at cosine of 150 degree. Using the property above, now let's sketch and find its reference angle. So here's our xy plane, 150 degree from standard position, it's right here. So this is 150 degrees, which means the reference angle is this piece right here. So that is your reference theta. So this would be 30 degrees. So now I can replace this with its reference angle, but we need to make sure to keep consistent with the sign. So we know that since this is in the second quadrant, cosine value in the second quadrant is negative because cosine corresponds to the x-coordinate. So this is equal to negative cosine of 30 degree. That's the reference angle. And then from memory, we know cosine of 30 is square root of 3 over 2. So this is negative square root of 3 over 2. So that's the value of cosine of negative 150 degrees. Number 17, we're going to sketch this logarithmic function by using transformations. So let's go ahead and do that. So here's our xy plane. And we know the logarithm of any base a greater than 0, positive, we know the shape looks like this. So let's call this logarithm of base 6 of x. So this +1 right in here, this means this is a shift. It's a horizontal shift to the left. So we're going to go left 1 unit. So initially, this function has a vertical asymptote at x equals 0. So if you go 1 unit to the left, then everything will shift 1 unit to the left. So I will shift the asymptote first so that it's better when we sketch it. So here's the new asymptote at -1, x equals -1. So then we'll indicate that by using dotted line just like this. That's our new asymptote, and the graph will shift 1 unit to the left, so the point 1, 0 now becomes 0, 0. And you just make the same shape, something like this. So that will be the graph of log base 6 of x plus 1. All right, so we got the graph. Now we want to label all intercepts, which we did. The point 0, 0 is the x and the y-intercept, and the asymptote right here, x equals -1, and state the domain and range. So the domain for this graph, it's going to be starting from the asymptote, open, -1 to infinity, since it's keep on going this way. And then the range, it's going to be all real numbers, -infinity to infinity, since the graph exists everywhere here along the y. So that will be the additional information we can also jot down just by looking at the graph. For number 18, we have another sketch to make. So we're going to be sketching 4 plus 1/3 to the power of x. I'm going to rewrite 1/3 in a different way. So you have, if you rewrite, it will look something like this. Y is equal to 4 plus 3 to the -1 to the power of x. And then by laws of exponents, -1 times x, that will just be -x. So this is 3 to the power of -x. Every time you have fractional base, you can always do that. So now we know that the exponential graph looks something like this when your base is greater than 1. So perhaps something like that. So it has a horizontal asymptote at y equals 0. This point right here is 0, 1. So let's call this is the graph of 3 to the x. Now, if I try to graph 3 to the -x, well, that means it's a reflection over the y-axis. So I will have a graph that looks something like this. So reflecting over the y-axis, something like that. That will be the graph of 3 to the -x, roughly sketched. So by reflecting, we don't change the asymptote or the intercept. And now we're going to go 4 units up because of that. So we take the graph and slide it up 4 units. So our new asymptote will now be at y equals 4. So I'm going to go ahead and just duplicate this and show you a new graph. So here's the duplication of this. And now we're going to slide everything up 4 units. So y equals 0. Now we'll be shift 4 units up. So let's call this 4. So sorry, this is a little off scale, just so that it fits in our screen. And then this point right here, if you shift it up 4 units, now it's going to be at 0, 5. So I'll just make a graph that looks right here. Let's make this the 0.5. And then the graph is just sliding through just like that, getting closer to the asymptote on the right side. So that will be the graph of 3 to the -x and plus 4. And this is the horizontal asymptote, y equals 4. And then after we finish sketching, so that will be the final sketch, we're going to state the domain and range. So the domain for this will be all real numbers, -infinity to infinity. The range will now be starting from the asymptote, and then the graph goes upward. So it'll be starting from 4 to infinity, open. So that will be the domain and range of this graph. For number 19, we're going to sketch this polynomial. So the leading term is right here. That's the leading term. So the degree is 4, which is even, and there's a -1 in front of it, which is the leading coefficient. So it's going to behave like this at the end. So that's the end behavior. So now let's factor. So f of x, you can factor out a -x squared. then the inside of it becomes x squared minus 9. And then x squared minus 9 can be factored further as x plus 3 and x minus 3. So the reason we needed to factor so that we can find these zeros. The zeros are 0, 3, and negative 3. Simply setting each of these to 0 and finding them. Okay, now that we got the zeros, now let's test them. So here you go. Let's plot them in order. We got negative 3, we got 0, and we got 3. So now let's see what are the signs between each zeros, and we can see if it's above the x-axis or below the x-axis. All right, the end behaviors, we know that it's going to be going down in both ends. So here and here, the graph lies below the x-axis. So we're going to put negative, negative, just like this. Now in between, we can either pick a test value within each interval, plug it into the original or the one you factored, or you can simply look at the multiplicity. For instance, if I want to look at this 0 and I look for which factor it came from, well, negative 3 came from this factor, and this factor has a power 1. It wasn't written, so it's 1. Odd power, that means the sign to the left and to the right of that 0 will change. So that means if to the left was negative, to the right will be positive. And then now let's go to the next 0. The next 0 we have is 0. Now 0 came from this factor right here. It has an even power, which means the sign to the left and right does not change. So it'll be positive again. And we don't need to do the last one because we already have it from end behavior. So that's how you do it quickly, figuring out what sign goes to the left and to the right of a particular 0. So here's our xy plane. Let's plot the zeros. Here's the 0, here's negative 3, and here's 3. So now since we're coming from below, so we'll have a graph that looks like this, and then we're going to be positive, go through the 0, make a tiny parabola, and then go through it. So something like this would be the graph of this function. So this is f of x. We're going to label all intercepts. They're already labeled. And then we're also going to describe the end behavior. All right, so let's go ahead and describe them. So the end behaviors are right here, are also right here, which we did earlier of this problem. So let's start with as x approaches negative infinity. So we can say that as x approaches negative infinity, the graph is going downward. So f of x is approaching negative infinity. I'm just going to slide this down a little bit, just like that. F of x goes to negative infinity. And as x approaches infinity, f of x is still approaching negative infinity. So it goes down in both directions, as we can see it right here. So that will be the description of the end behavior. All right, the last problem of this test is graphing this trig function. This is a sine of x. So we're going to transform sine x to graph sine of 1 over 2x plus 3. All right, so first thing you want to do is figure out the amplitude of this graph. So the amplitude of this graph is the number in front of sine, which is 1 in this case. So the amplitude will be 1. Then next thing you want to figure out is the period. Period meaning how long it takes to complete one cycle. So that would be 2 pi over k. And k is often this value right here. That's your k. So in this case, it's 1/2. So this is going to be 2 pi over 1/2, which is 4 pi. So it takes 4 pi to complete one period. So now we can also figure out the interval of one period. It's going to be, since there's no horizontal shift, it's going to be from 0 to 4 pi, since the period is 4 pi. And we can also write down no horizontal shift, which is also known as the phase shift, as being mentioned in the problem. We have a vertical shift, which is this number right here, plus 3 that you see in the problem, plus 3 right here. So this is up, so up 3 units. This is also known as the midline. So it's the halfway between the maximum and the minimum value of this function. All right, so we got everything written down. Let's take a look at the graph. So I'm gonna scale it this way since we're only going to graph from 0 to 4 pi, only one period. So the regular sine curve, without any modification to the period, it looks like this. So it starts at 0 and then it's bouncing this way. So let me try to draw it again. So this is the usual sine curve from 0 to 2 pi. And then we will figure out the rest. The amplitude here is 1. So 1, -1. Now that's not the one we're drawing. We're drawing the one from 0 to 4 pi. So this is just being stretched. So let me redraw that so it's better approached. So if you were to draw one cycle of what you just saw, it's just being stretched horizontally. So we'll complete one cycle. So I think I'll redraw this. Okay, so something like that. So the maximum here is 1, minimum here is -1, and it completes one cycle or one period from 0 to 4 pi. So this is the halfway between 0 and 4 pi. That's 2 pi. And this right here is halfway between 0 and 2 pi. And this right here is the halfway between 2 pi and 4 pi. It's 3 pi. Okay, now we're going to shift this 3 units up. So that's where we're going to get the new midline. So initially, this is your midline for the sine curve or the cosine curve y equals 0. So now if you shift 3 units up, new midline, it's going to be at 3 right here. So let's call that 3. So we'll draw the midline first and then retrace the graph. So you can simply just take the graph and retrace it. So I'm going to do my best to show you how this looks like. So one of the point is here. Then we have 4 right here. So that will be this point, and then this point right here moved 3 units. And then this one right here is going to be at now 2 right here. And then the last point, it's going to be at 3. And then just retrace the graph. So it'll look something like this. So this is how the graph of this equation looks like. And then, of course, the graph continues in both directions. So this is your new midline, which is y equals 3. And our final picture is this graph, not the one below. This is y equals sine of 1/2 x plus 3. And we're to label the maximum point and minimum point. This is your maximum point. So we can say that the maximum point, let's say the maximum point occurs at pi, comma 4. That's the maximum. That's this one right here. And the minimum point of this graph, it's going to be this one right here. So that would be at 3 pi, the y value is going to be 2. And you see how the midline happens to be the halfway between them. So from here to here and here to here. So as the graph oscillates, you will have a maximum value and a minimum value. All right, so this will be it. This is the end of this test. I hope this was helpful for you. I'll see you all next time. Take care.